Hi, I'm Bob Doyle, the information philosopher, webcasting from my ITV studio here in Cambridge, Massachusetts. I'm hoping to reach philosophers and scientists around the world to help solve some great problems in philosophy, in physics, in biology, and in psychology. I'm hoping to also reach any of you out there wondering about the deep nature of reality given to us by quantum mechanics and understand our place in the universe. We live in the information age, but I find that very few philosophers or scientists understand the nature of information, or an abstract quantity that I believe is the stuff of thought. Information is neither matter nor energy. Information needs matter to be embodied in our brains, for example, and it needs energy to be communicated, like this lecture coming to you over the internet. But matter and energy are conserved quantities. It may be hard to believe, but the total energy and matter in the universe today is the same as there was at the beginning of the universe nearly 14 billion years ago. And if the stuff of the material world is just a fixed total amount, what can possibly explain all the evolutionary change that we see? These changes are in the information and the order in the universe, which I will show have been increasing since the beginning of time, despite the second law of thermodynamics, whose increasing entropy is said to destroy order. The changes are simply the arrangement of the atoms and molecules into what I call information structures, like the galaxies, the stars, and the planets. Stars, though, are simply passive objects under the complete control of physical forces like gravity, whereas living things, you and I, are dynamic and growing information structures under our own control, by our own minds. I'll show that we are forms through which matter and energy continuously flow. And I'll show its information processing from the DNA in our cells to the thoughts in our mind that controls those flows of matter and energy. I'll argue that information can be thought of as the modern spirit, the ghost in the machine, the mind and the body. It is our souls, and when we die, it's our information that perishes. Our matter remains. I will argue that information philosophy can also explain many mysterious aspects of quantum physics, like the Two-Slit Experiment, the collapse of the wave function, wave-particle duality, and entanglement, which claims that a cat can be simultaneously dead and alive, that one object can be in two places at the same time, and that information can travel faster than the speed of light. Working through the thoughts of Albert Einstein, I hope to show you that such spooky action at a distance, as he calls it, is simply impossible. Now, my work on information philosophy is available to you in many forms. My website at informationphilosopher.com, my books, which are in print on Amazon and free online as PDFs of each chapter, and through these lectures. Now, today's lecture is our usual Wednesday, the subject being I choose one philosopher or scientist from my long list of 200 philosophers and nearly 100 scientists on my Information Philosopher webpage. Let's take a look at that webpage for a moment. And I can scroll over. I'm trying to learn some new tools. I can scroll over to the left side here and see this long list of philosophers. This is the result of 60 years of study, many books read. I've taken the arguments of each of these thinkers and put them on these pages, along with particular references, quotes from their work, so that you can go and get the resources you need to understand this field, this thinker, in each case, from my website. My whole goal is to put out what I know and what I think is the best understanding of all of these thinkers. And so when we come to the bottom here, we're in scientists, and today we're going to be looking at Richard Feynman. Now, Richard Feynman is very famous for one thing, and that is that there is a mystery in quantum mechanics, just one mystery. And there are people today who say there are multiple mysteries in quantum mechanics, including entanglement, as if that's a brand new mystery uncovered by Bell's theorem and the concerns of Einstein that particles might separate and be able to have influences sent from one to the other. By measuring one, there would be an influence that would go to the other, no matter how far it was away. But I hope to show you that Feynman has it right, that there's basically only one mystery in quantum mechanics, and that mystery can be understood in terms of this famous two-slit experiment, or two-hole experiment, as he described it. So let's go to Feynman's page. Well, first, before I go, I love to kind of show you that I'm trying to develop my tools, my ability to show you different web pages, and even the website itself. Let me just go back for a moment to the home page. And over here I will show you, I'm basically scrolling down this home page. It will take us to the top. And I want to just, oh, there we go. I've got a strange behavior in the mouse. Now I'll move over to the right in this page. Bear with me as I learn to be able to do this on the web. And I wanted to show you that I've, in the last few days, just set up a new set of links on the home page, which lets you go to tweet if you want to about some page I'm working on, or if you want to like a page on Facebook. And here there are little links to follow. These send you to, for example, my Twitter page, which you can then click on to be a follower, which I'd appreciate, or Facebook, or my YouTube videos page. And now I've just added another little link, which has a WordPress icon, to tell you that I have organized all my videos on WordPress, which is a chronological blog of all of my lectures. Let's just go back for a moment and take a look at those blog pages. This is the announcement of today's lecture. Here is the blog. It has the same heading as my regular website and a few drop-down menus. But the main thing about a blog is that here's this one, which is December 13th today, and the topic Richard Feynman. But if you scroll down, you see here we are, December 12th. This is what we spoke about in our free will lecture yesterday, Tuesday, on how we need to separate free will from moral responsibility. And it has the diagram and the important notes of what I was going to do. And lo and behold, this is really quite wonderful. I'm very happy I'm getting there with this, that I've got the actual lecture, yesterday's lecture. If I hit on this play icon right here, I'll be able to bring up that lecture. And so it goes. I go back to my Monday lecture. And here I've got some descriptions of the two-slit experiment, which we're going to visit again today, because Feynman is the one who told us this particular experiment is the source of understanding the one what he called the one mystery in quantum mechanics. So here is my Monday lecture, and we were looking at different animations to try to understand the two-slit experiment. And then we're back to December 8th, last Friday. Here's a lecture on Einstein, on how he discovered wave-particle duality decades before Heisenberg and Schrödinger in the late 20s. So let's see. Let's go back to Feynman's page now. And this page is my web page on Richard Feynman, which we could get to by scrolling down the left-hand side, all of my philosophers and scientists, and find him. It would bring up this page. Now, Feynman is an enormous figure in the history of quantum mechanics, the actual work done. He won a Nobel Prize for what's called quantum electrodynamics. He successfully built the quantum theory of the electromagnetic fields, and he did a lot of other very interesting work in earlier years. He developed, I think I have a little section on this on the page, he developed what's called the path integral formulation of quantum mechanics. And just to kind of see the depth of this thinker, he was an extraordinary, entertaining and exciting proponent of various ways of working on problems. One of the famous things he did was invent these things called Feynman diagrams that I won't go into here, but they were started off by this attempt to have another formulation of quantum mechanics. Now, this is not another interpretation of quantum mechanics, trying to understand it. Famously, we'll see in a moment that he says nobody understands quantum mechanics, but he did develop tools that allow us to calculate quantities in quantum mechanics, which really were begun by Werner Heisenberg, Max Born, and then Erwin Schrödinger, whereas Heisenberg had an idea that he called matrix mechanics. Actually, Born named that because he was an expert in matrices. And then Schrödinger developed what we call wave mechanics. And already the emphasis by Heisenberg was on particles and detecting them and energy levels and so forth, and a picture in which electrons initially were moving around orbits in atoms was developed by Heisenberg into just focusing on the observable quantities going in and out of atoms, namely the spectral lines, the hydrogen spectral lines, which we will deeply look into at some point soon. Whereas Schrödinger decided that you could ignore the particles. He didn't even believe there were particles. He argued there were no quantum jumps between the energy levels in the Bohr atom, that somehow these things could be all explained away by focusing on waves. And that distinction between waves and particles we saw a couple days ago was something that Einstein had discovered and was very concerned about, starting as early as his 1905 paper, and then especially the 1909 paper, where he had the waves going off in all directions, and yet particles landing in just one single point at the end of the experiment. And this is a major thing that, Richard Feynman turned to in his famous lectures on physics. I should have brought his book down to show you this wonderful 3-volume set called Lectures in Physics, but I did bring down Feynman's Cornell lectures at Cornell in the late 60s when he'd more or less completed those lectures, and he summarized 6 of those lectures in a book called The Character of Physical Law, and was also released. Quite lucky for us, it was filmed on film at Cornell for what are called the Messenger Lectures, and we'll use them today to try to get a flavor for Feynman and how it is he works. So coming back to the path integral formulation, which I have here for a moment, this is sometimes called his sum over paths. Let's see if I can bring this up on my other screen for just a moment. Here we go. Scroll down to sum over paths and see how good I am at navigating here. Let's go to this page. And again, move the page over a little bit. And then I'm able to do things like double click and highlight the phrase sum over paths. This is something I've been trying to do for quite some time. And with my little Surface Pro units, which I'll remind you what they look like by going here. You see I'm sitting in front of my switcher, which I use to go between scenes, so I'll go to myself view this way and then back to myself looking down from the side here, seeing my whole studio with monitors in the back of the room and my teleprompter on the wall underneath every camera. And down here I've got, beside my switcher, I've got a screen that is a PC style screen. That's the one that has the sum over paths on it right now in the path integral formulation of quantum mechanics. That's a real PC, and I can highlight phrases, which is very nice, but I cannot do that on my Surface Pros. They let me resize things. Let's see if you can see that. Probably you can't see that very well. Let me come back to my view here. And you see what I can do in terms of resizing a page so that you look at a particular part of it very closely. And that's great, but I can't touch on a single phrase like sum over paths and have that show up for you like I can over here on the regular PC. So I'm struggling to get a combination of tools. Let me go here for a view. I'll dissolve over to this view. I'm looking for a combination of tools that will allow me to let you see what I'm doing and actually be able to do something to focus your attention on a particular thing. So let's go over from to my PC again, where we're looking at the sum over paths. And what it was done, what Feynman did was look back to an article in 1933 by Paul Dirac, who had been part of the original team in the 1926-27 time period who developed quantum mechanics. And Dirac developed the most elegant formulation of quantum mechanics in terms of what he called bras and kets and expressions that encapsulated the calculational techniques of why it is a particle might jump, or there would be a quantum jump between one state and the other state, and that jump would be evaluated as an operator that described the property changing, like the position of a particle, between two states, the initial state and then the final state. And this gave us it came down directly from Werner Heisenberg. It was a view that there's a great array of states, or a large number of states, let's say, from starting here, 1 over to n, or it could be an infinite number of them. And you could write that at the top of a square array, and you could write down the left-hand side the values of the states it could jump to from 1 to m. And then any individual jump somewhere in the middle would be an element in what's called a matrix. So Dirac, in 1927 or so, had done this formalization of the work of Heisenberg and Schrödinger combined. And then in 1933, he decided to take a different approach to the fundamental mechanics of matter. And used what's called a Lagrangian formulation, sorry for the technical terminology, compared to the Hamiltonian formulation, which had been used by Heisenberg and by Schrödinger. And when he did this, Dirac was able to take advantage of a concept called the least action principle. It's an idea that if there are many paths that a particle might follow, it's going to follow the one for which a certain quantity, this Lagrangian quantity, is called the action. It will take the least action to get from point A to point B. And by doing that, Dirac came up with an alternative formulation. You got the same results, but you had a different insight as a result. As an expanded version of looking at what's going on. So what Dirac did, what Feynman did then in 1948, I believe, is to replace the Hamiltonian with the Lagrangian, and then taking the idea that there's a single path for the quantum system. Let me go back over here to the appropriate sentence I want your attention to be paid to. He takes the idea of a single path for a quantum system. Now let's, for example, consider the path of an electron or photon going through the two-slit experiment. We'll come back to this later in this lecture. The question becomes, is there a single path that the electron takes when we fire it towards the two slits, so that it always goes through either one slit or the other slit? Because there's no way for an electron to split itself into parts and have part of it go through each one. But if it can't go through each one, how is it that we get this strange interference pattern at the back of the experiment? We're going to now look, instead anyway, what Feynman did was say, let's imagine adding up all the possible paths, an infinity of quantum mechanically possible paths, to compute the probabilities of what's going on. And this corresponds to the wave picture of waves going in all directions that Einstein worked on, as we saw, and he doubted that that was what was going on when he formulated his hypothesis that light comes in a quantum or a photon in his 1905 paper, and then in 1909 when he just questioned what it meant to have both wave and particle views of what's going on in quantum reality. So let's see if here I can go to this famous phrase, famous statement by Feynman, excuse me, that nobody understands quantum mechanics. And with luck, I've put in here a link, usually in my papers on my website, and you'll see a blue link. It indicates there's something here. So let's just click on this and see what happens. And I've got to do two things. We hope I've got the quote with him talking about nobody understands quantum mechanics, but I wish I could turn on the closed captions. Unfortunately, I can't turn on the closed captions until I get the thing playing. So I go there, then I hit the closed captions here, and with a little luck, we'll hear.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
So now the question is, do I go back to... Can I get back to my Feynman page? And I can, and that's great. So as I give you this lecture, I'm happy to say I've been able to add important elements like quoting Feynman not just with a sentence, which I have right here. Let me show you that. I'll go to my right-hand screen, and here is that quote in words. But if you notice, oh, I see, that's not the nobody understands quantum mechanics. Excuse me, I'm showing you a quote on his claim that the two-slit experiment, with particles, whether they are electrons or photons heading down towards two slits and going through, that experiment contains the one mystery, the important one mystery of quantum mechanics. And that's right here. The two-slit experiment contains the one mystery. And he says, I will take this one experiment, and now I see I'm not getting that on my screen because I can't do that. Let's see. I can do it here. He's going to take this one experiment, and now I want you to focus on this claim because it's a basis of a huge amount of work in terms of getting to the deepest possible understanding of quantum mechanics. And let me point out that I have a quote where this comes from a book called The Character of Physical Law. So let me just take a moment and go to my desktop where I have a camera over my head and show you that I brought my copy of The Character of Physical Law. And in the 6th lecture, which is called Probability and Uncertainty, I find the really most wonderful description of the two-slit experiment. But here on page 129, here's the quote we just had. There's a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time, and so forth. And he comes to the conclusion that although people did, eventually many people understood relativity, that he can safely say that nobody understands quantum mechanics. So here's the book, and I've put this on the website, so you don't have to own the book. And on the next page, we see him describing the two-hole experiment, the two-hole experiment, he calls it, rather than two slits, in which there are electrons or light sent off and going to a wall where there are two openings in the wall. And he shows how if only one hole was open, let's say we block this one, then we would get a pattern coming through that slit and making a bump right in line with that slit. And that if we close this slit, we would get another pattern like this, more or less in line with the second slit. And then he describes it as, well, if we did a few electrons or photons coming through this one for a while and then close this one and open the other, we'd get the other one, and they would two form together this shape in the middle. So we'll be getting into that and again in a moment, but I want to just say how important that Feynman takes this to be. He's going to tell us that this is the core one mystery in quantum mechanics. So let me go back here and stay with this book for just a moment. And he says, I'll take just this one experiment which has been designed to contain all of the mystery of quantum mechanics. Just an amazing claim to me. To put you up against the paradoxes and mysteries and peculiarities of nature 100%. So the way Feynman likes to talk, down-to-earth terms. Any other situation in quantum mechanics, it turns out, can always be explained by saying, quote, you remember the case of the experiment with the two holes? It's the same thing. I'm going to tell you about the experiment with the two holes. It does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form. Okay, so what I want to do is tell you that where I've found this quote, where I've found this argument by Feynman, and then I've put it on our website, and we're now looking at it there. And I've also, if I can find it here, I'll just zoom in here for a moment. I've also added this link. Let me, again, I think we can probably see it better if I go to this page and go down below the quote that I've just read to you out of the book and see that I've put here a link. Watch the video. So let's see if we can do this again and if I can turn on the subtitles properly.
And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%. Any other situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with the two holes, which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form. So I start with bullets. Then all the experiments are going to be in the same general design, so I'll...
Okay, so let's see whether I just am able to bring up this one. Here he is on the wall behind us at the end of this quote. I'm getting a little better at controlling what you're seeing and what I'm talking about. And we now have Feynman telling us first, nobody understands quantum mechanics, and then the reason for the lack of understanding is because at its base it has a mystery, and he's going to argue that that mystery is contained in this one experiment called the Two-Slit Experiment. We saw a brief picture of his argument there. Now I'd like to go, see if I can find the right page to bring this up. I'd like to go to this one here. I'm working with this one. here. And this is my page on the two-slit experiment and the one mystery. Now, I think I'd like to bring that up on
Draw it this way. Suppose that we have some source of bullets, which is just...
And bring the screen down here and do the same thing over here. And, okay. So the two-slit experiment, as we see at the beginning of this page, is, I'd like to find this page over here. It's quite a challenge for me to drive around sometimes. So I have it here. Now switch to this page and see I brought it up on another screen. And this screen, I can also expand it. Bear with me while I learn to do this. Push the mystery off that way, and then control the page over so it more or less fits on the screen. And we start here with where we've been with our links to the Feynman page and our links to YouTube videos of his lecture and quotes from his lecture. And here it repeats itself, but I don't yet have on this page the video for you to play. But this is the sort of work I do in between lectures. I go and add links on a page like this one, on the two-slit experiment. So you could probably find on this page as well, which is located in a section called Experiments and Solutions and so forth. You should be able to find here that quotation by, you find the words here, you should be able to find the video. That requires me to add this to my web pages, and I now have thousands of web pages, so there's a good deal of work involved in making available to you quickly and easily on one single page or a couple pages. So the Feynman page is what we were just looking at with his video inserts, lecture quotations. Quotations now in the sense not just of words like we have here, but quotations with Feynman himself speaking to us and telling us what it is he thinks is going on in quantum mechanics. And remember, he says, I'm going to tell you what is happening. I am not going to explain it. And I don't think you should try to understand it because, quote, nobody understands quantum mechanics. Okay, now I have a slightly different view. It's actually 50 years after the work of Feynman's lectures on physics and his Cornell lectures. And to be frank, the explanations he gave are still the fundamental standard lectures, explanations, or shall we say, descriptions of what's going on in quantum mechanics and our experiments. Let me just turn this down for a moment. My music track just started up for a reason I'm not sure. So Feynman has told us given us a description, a careful description of what happens in a two-slit experiment, but he's told us, don't try to understand it. Now, my work on Einstein, which we do every Friday on my next book, half of which is available to you on the web, I believe Einstein always had a different view of what was going on at the quantum level. He described his view as, quote, objective reality, that somehow down below, the particles were real, they were localizable in one place, where the founders of quantum mechanics, Heisenberg and Schrödinger, thought of these particles as fuzzed out and possibly at indeterminate locations, even multiple locations at the same time, because the wave function is giving us a picture that the particle of light or matter is spreading out until it doesn't. And when it doesn't, when it stops spreading out, it suddenly is found in one location in the experiment. This led those founders to describe what they call the collapse of the wave function. And the two-slit experiment, well, it isn't exactly obvious what's going on there. I want to make an illustration for you in which we show that the collapse, that the wave function is there in all space, describing the probabilities of finding a particle somewhere, but the instant the particle is found, it felt to them as if that probability wave had a substantial nature to it, which must have collapsed at the one point where we found the particle. So my work is taking off from Einstein's sense that the particle probably had a definite path, but one that we cannot see, one that we cannot observe, and one that we cannot predict, and one that we cannot measure without interfering, bad word, without destroying the interference patterns that we see in the two-slit experiment. That's a lot of work for me to explain, period, in my books and on my website. And it's going to be demanding for me to explain it to you, but I'm going to do my best. And as I go forward with the lectures, I hope to develop my very best set of arguments for this. And later lectures, I hope I'll be able to deliver them, these ideas a little more succinctly, shall we say. Okay, so here I have an animation, and let's see if I'm actually moving it. Nope, I'm on the wrong screen. So let me go to this screen. Here I have an animation of the two-slit experiment, and you see it's moving slowly through its animation. Initially, there's one slit open in this picture, and then there's a little yellow dot to show where light, part of this one single bump that Feynman showed us, was giving light and landing with light here. But now we've opened the second slit and closed it. Now we're back at the start again. Here's the little spot where there's light coming in proportion to that bump. But as we open the second slit, the interference pattern changes to multiple what are called interference fringes. And as I close that second slit, we come back again. So let's go through this one more time. Notice the three fanning out kind of light areas which correspond to the little satellite fringes. And now instead we have lots and lots of fringes and lots of fanning out areas. Now we're coming back to the one slit open. Here are the three areas of what are called constructive interference. And once again, I'm going to open the second slit, and we're going to see many, many, many bright sort of rays or beams going out. Then we come back to one slit, and we see there are only three of those. Okay. I like to argue, and this is perhaps the most stunning thing, that when we open the second slit, okay, we have only one slit, there's plenty of light where this yellow dot is, but when we open the second slit, that light that was right here at this location goes away. Now, how do we confront that on a logical basis or a physical basis? One slit open, plenty of light all around here. Open the second slit, and as it comes fully open, there's no light at all landing where I have the mouse right now. So I've written that over here, and I say, perhaps the most non-intuitive aspect of the two-slit experiment. Let me come out so I can be, I'm on the wrong screen here, so I'll go back to this one. And I need to go over here for a moment and get that on my satellite screen. What I'm saying here is, I believe, a distinct step beyond what we've heard from Feynman, in the sense that he certainly appreciated this, but I want you to appreciate it because it seems so non-intuitive. He's told us there's no understanding here. And part of the no understanding is we're asked to believe, or I'm going to show you. Feynman has given us this set of ideas. I've animated them more than he does. He basically is armed with a chalk and a blackboard, not even a modern whiteboard with a black marker or whatever. So he had relatively primitive tools to explain things. Now, I'm very lucky. I can draw these animations. I've drawn them myself, but I'm hoping to get animators to draw even more beautiful ones that'll illustrate what's going on here. But I think I've got the fundamental aspects of what's going on. With one slit, we have light, and when we have in a smooth one big bump, and that's about to appear right here. So we're coming back to the original with one bump, and then constructive and destructive interference. And as we add more light and the multiple interference fringes, there's one spot in here where there's no light at all. So what I write here on the left is to say the most non-intuitive aspect of the two-slit experiment is when we first note the pattern of light on the screen with one slit only open. And we have that yellow dot at the start of the animation. We'll see it coming back right now. There's the yellow dot where the light is definitely hearing. But then we open the second slit, admitting more light into the experiment. But we observe that some places on the screen where there was visible light have now gone dark. And this happens even when we are admitting only one particle of light at a time. Now, as any of us learn enough about a problem to appreciate the problem, and that's what Feynman is trying to do with us, show us the strange, non-intuitive behavior, I think this particular aspect has to be one of the deepest, most non-intuitive. How can it possibly be that as I open this second slit right here, and I admit more light into the experiment, that it causes less light? Here the light at the back is everywhere under that large maximum, and yet when I open the second slit, there are bright fringes, but there are dark fringes in the middle where no light has appeared. How can it possibly be, from the perspective that we're sending just one particle in at a time, one particle in at a time, one particle in at a time? Nevertheless, the opening of the second slit, through which, by the way, we think the particle might have gone through one slit or the other, but the mere fact of the second slit now erases or darkens the light in this one spot where the yellow dot was a moment ago, and it becomes dark. How can we have light falling on a screen, add more light coming through a second open hole, and have the light disappear at that one spot on the screen? If you can understand that enough to describe it to a friend, say that Bob Doyle, the information philosopher, tells me that I shine a light in, and when I add a second light in, the light goes away at some points in the experiment, you will have your mind grasp one of the most difficult things to understand about this. It seems as if it was waves, you would understand how the waves go through both slits, and then the waves, the crests of one cancel out against the crests and troughs of the other, and you get points where there's no water wave. That's understandable from the wave point of view. But it seems like the utmost mystery how that could be the case if we're sending a single particle into the experiment and then another single particle, and we're just always single particles. There's never an opportunity when the particles can interfere with themselves from the perspective of having gone through the other slit. All right. Here's the original diagram that Thomas Young drew in 1802. We've seen that before. But I'd like to go down and look at some other spots here. Here's just the left-hand illustration that I had, showing one slit open, showing the rays of light area where the two waves, okay, the one coming from one side of the slit in this case and the other side of the slit in this case, work together to constructively interfere and make a, here we go, a bump here. Whereas in this area, we have this darkening where the crests and troughs of the two waves from the one side and other side of the slit are interfering with one another and not agreeing, and we get no light at the back wall there. So let's see if I can go back to, let's just turn back for a moment to Feynman's little book and show you that he imagined that if we did one slit, we'd get this one bump, and if we did the other slit, we'd get this other bump. Now, he doesn't add the little bits of destructive and constructive interference at the edge, but that's okay. Let's come back here and see that this is what Feynman was just describing as a bump lined up with one slit. And then he imagines, well, what if you had a bump coming from one slit and another one coming from the other slit? Let's go back and take a look at his picture. Maybe I should turn it so that I'm trying to show it the same way. And he's showing how those two will add up. Well, the math of it actually is that if they're close enough together to give us the maximum kind of interference when they're both open, it turns out the sum of these two above looks more like one big one, which is interesting to me, a little more accurate than what Feynman put in his lecture. Also, I've shown a kind of bands of dark and light. Perhaps I should have made this the light area and not the dark area, and that would be more intuitive. You'll see that's what I did below. Now we come to the second view. And in this view, once again, I just want to draw your careful attention to the fact that we can see these areas of constructive interference going off, and they get all washed out going way away from the center. But here in the center, you can probably pick out these zones of constructive interference. And one big thing that's impressive, the maximum amount of light, which formerly was behind a slit, okay, or behind this slit. Remember, they were these most light going here for the left slit, open only, most light going here for the right slit, open only. Suddenly, we have a shape like this, but what we see when they're both open at the same time, it's sort of got the same shape as above. Now, my drawing isn't just as nice as it could be to have exactly the same height, but you get the picture. And now we see that the maximum, as we noted above, when you have light from the left slit only, and right one is closed, and then you turn off, close the left slit and open the right, they do add up and they create something in the middle. Well, that's exactly what happens here. With the two slits open, the maximum amount of light falls right in the middle, not behind either slit. And here are those null points which did have light in them when we had the one slit open at a time, or when we had the two slits open at alternate times. If you open one slit, you see a little bit of interference out at the edges, but mostly a large central maximum. And if you open the right slit, you see the same thing, but over on the right. And now when you open the two of them, you see the interference, which cannot seem to be explained if only one particle is going through at the same time. So, okay, so here I've tried, and this is something I drew just 2 days ago. We discussed this as a problem, and since then I've decided to draw a kind of a light pattern, like the light falling on the back wall, to show you that when there's a maximum here, that's what it really looks like on the back wall, is light bands or interference fringes, these bands. We saw some of those in our YouTube videos on the two-slit experiment, and I'd like to be able to connect that up. But now I put the two side by side, and I basically am asking this question or answer, why it is that interference show up when both slits are open, even when particles go through just one slit. But we cannot know which slit it went through, or we actually lose the interference pattern. That is to say, the mere knowledge of which slit it went through is enough to destroy the interference and take us back to that picture. If we know it went through one slit or the other, we get this kind of a picture for thousands of photons or electrons. But when both slits are open, I pointed out the maximum is now at the center between the two slits, and there are now more interference fringes. And these probabilities now, and here's the new thing that I am hoping to add to this discussion. I'm trying to say that these waves, I'll come over to my cell phone screen, these waves in here are fundamentally, in quantum mechanics, not the water waves. They are the solutions to the wave equation that Erwin Schrödinger gave us, and they have high spots and low spots, interference, which gives null points where nothing is predicted and so forth. And Max Born came along, and using an idea that Einstein had thought of without publishing it, but he told a lot of friends, and I think we can see hints of it in some papers, which I'm trying to locate when I do the book on Einstein's work. These waves are probabilities. They are, because quantum mechanics is a statistical theory, says Einstein. It can tell us nothing about individual particles, so we can't ever know the path, the slit through which a particle will have gone, or its path getting from the slit to the back wall. These are not knowable, and Einstein described this situation as saying quantum mechanics is, quote, incomplete. It doesn't know all of what classical mechanics told us that we should have been able to know, that the path of a particle when we fire a projectile is completely predictable, completely knowable. But when a particle like an electron or a photon is sent into a wall and then into this two-slit experiment, we don't know them. But what we do have is this wave equation, which gives us a set of probabilities about the various possibilities. So think of the possibilities as the locations on the back wall. Think about the probabilities of landing at the different places as given to us by the solution to the Schrödinger equation, which gives us this wave pattern throughout the experiment. Now, these patterns are here given only the geometry, the boundary conditions of the experiment. They don't depend on whether a particle is coming in at the moment. Okay, this is now a deep forward step, I believe, in our attempt to understand quantum mechanics as a statistical probabilistic theory. We know the probabilities by solving the Schrödinger wave equation. The waves are actually just mathematical probabilities, pure abstract information. And as an information philosopher, I find this a very powerful way to think about this problem. The probabilities are abstract information about where we will find particles when we put thousands of them in and let them land on the back wall and expose a photographic plate or a CCD or whatever. So the waves are abstract, immaterial information about where concrete material particles will land if you do lots of experiments and get the statistics of the experiments. So coming back, in using more ordinary terminology, the wave equation is a prediction. It is a theoretical prediction. Theories are theories, they are predictions. The measurements of where the particles land, given thousands of them, are experiments. So theories are just ideas. Basically, in our head, they are knowledge about possibilities. Knowledge about possibilities is translated into exact probabilities using the wave equation. That gives us information, but that's abstract, about where concrete particles will land if you do a lot of experiments. Okay? So maybe one more time. This is a thing I want to be able to learn how to articulate and to explain with these pictures and others I hope to develop. And I love the web because I can do it visually nicely in a way that in print you've just got the one solid picture on the page, and you may or may not get to see where I think the important understanding might be. But this is, I believe, an attempt to understand beyond the ordinary conversation out there about waves versus particles, that somehow quantum objects are waves and they are particles, and they're one sometimes and one another. Instead, I want to sort these out and tell you that the waves are theories, predictions, they are ideas. They give us an idea in our heads about where we are going to find concrete objects in the quantum world. The waves are not the objects, they are not the particles. The particles are material. The probabilities about the possibilities for landing are not material, they are immaterial, They're information in our minds, like the information in our cells from the DNA, which carry instructions on how to manage and maintain a living thing, like our body, which I try at every opening of my lecture to point out, is not our matter. We are not our matter. We are not material. We are partly material. We have matter. We have energy coming through from the food that we digest that ultimately comes from the sun and so forth. But we have the spirit, I call it, basically the ghost in the machine. I have the control of living thing coming from the immaterial information, which is encoded in our DNA or embodied in our minds as a result of everything we've learned in our lives. We are living things, organisms that manage our affairs using ideas, which for me is simply abstract, immaterial information about what's possible in the world. Since William James first articulated it, he says these ideas that pop into our heads give us alternative possibilities for our action and our choice. And when we select from among those alternative possibilities, we do so in a way that is truly free, and the willed choice, the willed decision, and the willed action that follows is quite distinct from the free part. So we separate free from will, and we also separate free will itself from moral responsibility, as we said yesterday. Okay, so now I think we're coming up on our last bit of time here, and I want to just turn this thing a little bit up and say, again, thank you very much for listening to this lecture. I'll put up my email address and hope you'll communicate with me sometime about any questions you have about what we're doing. And I am now coming up with an idea that I will offer to philosophy professors and science professors the opportunity to have one of my lectures come into them live to their classes via Skype, and that would give their students and the professors an opportunity to interact with me and ask some questions and get them clarified, and it would be a way for me to be known by students who are young. 60 years ago, when I taught my classes of 30 students at Harvard, it was a great privilege to have them wrapped, very interested in the class, because they had to pass the class in order to get their degree and so forth. But today I'm hoping, beyond the 30 students I used to have in my astronomy classes, I could perhaps find individuals out there who, wherever they are just as interested, only because they want to know what's going on in the deep nature of reality, as I put it. And as a cosmologist, I'd love to be able to tell many of you how it is the whole universe came to be and came to have information structures in it, like the galaxies, the stars, and the planets. Thanks to work with some of my colleagues at Harvard, I have explanations of these things that are really worth hearing, and I cast them all in terms of the information that's created when a structure like a galaxy comes together out of dust and gas, when very large volumes of gas and dust somehow collect together into a beautiful spherical star or a planet like ours, and how it is that star could have the source of energy that it provides to us on Earth so that we can be living things and have a supply of energy, which is only coming as long as the sun is shining for us, and can have matter. Now, the matter is not no more of it being produced nor the energy, but it is flowing through us, as I say, because we are forms. Our spirit, ourselves, are ideas in our minds, and immaterial information about how our cells are working to keep us alive. So I think that's where we want to be for today, and I hope you'll join me again tomorrow for our lecture on metaphysics. And I think what I want to do is Perhaps put up my nameplate for the end. I'll say goodbye for now. Thank you. And we're at 45. And I'll turn this one down, and I'll say stop.